This is also the time to thank my mentors all along these years. I was fortunate to be introduced in the area of heterogeneous catalysis and surface science by John Black and Johannes Mott at the University of Michigan. They gave me enormous opportunities, and I very much appreciated the freedom to follow my own inclinations in modeling surface phenomena. I then had the outstanding opportunity to work with two world-class scientists, that is Mark Bardow and Jens Nordström, at Delaware and Denmark, the Technical University of Denmark in Linköping, where I learned how to look at the phenomena happening and underlying heterogeneous catalysis on the atomic scale. Subsequently, I was even more fortunate because I joined the Department of Chemical Engineering at the University of Wisconsin-Madison, where I had the pleasure to be, the honor to be a next-door neighbor of Jim DeMasi. And those of you who know Jim, you know that he's probably one of the most creative people that we have in the area of heterogeneous catalysis. At the same time, he has an outstanding sense of humor that makes everyday life much more comfortable. Finally, I'd like to thank a mentor who is not a catalyst person, but has been an outstanding mentor for me. And those of you in the chemical engineering profession will recognize his face. This is Bob Bell, a giant in chemical engineering, who has been an unbelievably kind and supportive person throughout my career at Wisconsin. Of course, I wouldn't be standing here unless it was for my hardworking students and postdocs all along my career. I don't have the time to spend going one after the other here. I have put together all of their figures. Here are my PhD students, past and current, the same with my postdocs, master students, same students from Europe mainly, and then a number of undergraduate students. I'm proud of them as well, because 90% of them have been engaged in the research careers leaving my book. So they are in graduate school or they finished graduate school already. I'd also like to take a moment to thank my research collaborators, starting with Jim DeMasi, Jens Nordström, Tom Keyes, Raj Majic, Mark Bardow, Flemming Giselbacher. I could go on for a while. Many of you are in the audience, and I want to thank you from the bottom of my heart for all the contributions that you have made to our research to make sure that we develop insights that we couldn't develop with our tool set alone. Collaboration is the way for me for the future, and I want to thank each one of you for your fantastic contributions to our program. Thanks to our financial sponsors, primarily DOE-DS, NSF, and also DOE for sponsoring the large number of supercomputing centers that we have been using all along. And finally, a word of thank you to my family. If it weren't for these three persons, that is my father, my mother, and my sister, I wouldn't probably be able to focus my energy to scientific interests alone. To resolving all these day-to-day problems, even far away, I'm really thankful to them for giving me the opportunity to pursue what I really like. So thanks for standing with me by now. What I'd like to move on is to the scientific part of my presentation. I will cover two topics. The first topic is the water-gas shift reaction that has to do with hydrogen production and purification. The second reaction is a hydrogen purification reaction, that is a preferential oxidation of CO in the presence of hydrogen. The water-gas shift reaction, I will discuss aspects of the reaction mechanism. I will illustrate trends among different metals and identify reactivity descriptors that say what is a good catalyst, what makes a good catalyst for a water-gas shift reaction, the key characteristics of a good water-gas shift reaction. In the second part of my talk, the preferential oxidation of rocks, preferential oxidation of CO in the presence of hydrogen, that is PROX. I will start with saying a few things about the reaction mechanism, and then I will show you how one can use first principles methodologies in order to identify promising catalytic materials. In particular, I will call them core cell nanoparticles in a moment. We will then see that how our colleagues were able to synthesize those core cell nanoparticles and subsequently test experimentally those nanoparticles, providing some hope that there is some further reactivity enhancements that we can achieve by exploiting nanocomposition and nanoarchitecture. So here is a typical chemical engineering flow sheet diagram, whereby you start with air, fuel, and water, steam in the form of steam, and one of the fuels that are shown here as an example could be methane, methanol, ethanol, gasoline, and then you use a heterogeneous catalyst, for instance, based on nickel. At the exit of the reformer reactor, you get about 45% hydrogen content and then 10% CO content. If you were interested in feeding this particular hydrogen as a fuel for a PM fuel cell, then you might have a problem for sure, because this CO poisons the anode side of the catalyst. So you need to clean that hydrogen before feeding it to a PM fuel cell. The first line of attack that people have been using is the water gas shift reactor, whereby you use a mild oxidant, that is the water molecule, to get CO2 and hydrogen. And then this is carried out in two stages. Typically, one is the high temperature water gas shift reaction based on iron oxide catalyst, and the second one is a copper zinc oxide aluminum supporting a catalyst that is carried at low temperatures around 250 degrees C. It turns out that I will spend some time discussing the low temperature water gas shift reaction mechanism with you today. At the exit of this reactor, you get an enhanced content in hydrogen, reduced amount of CO, approximately 0.5%, which is yet pretty high, so that you need to implement another reaction, another reactor, if you wish, the preferential oxidation reaction, so that you can cut down to ppm levels before you can provide